Hello and welcome back to Advent of Code 2023, day 18. Um, I don't like that. Oh, hang on, let me change these lights. I don't like that light appearing on my cupboard. Yep, that's not good. Wait, there's one more light I can use. Yeah, there we go. All right, so day 18. Lava Duct Lagoon. All right, as always, I'll just grab my coffee quickly. Uh, okay, I'm done. I've got it. I almost accidentally made a second copy. Alright. Thanks to your efforts, the machine parts factory is one of the first factories up and running since the lava fall came back. However, to catch up with the large backlog of parts requests, the factory will also need a large supply of lava for a while. The elves have already started creating a large lagoon nearby for this purpose. This feels like something out of Minecraft. Storing lava in a huge lagoon. No. It feels like Dwarf Fortress, actually. This is such a Dwarf Fortressy thing to do. Which, of course, is the game that Minecraft was based on. The elves... Okay. However, they aren't sure the lagoon will be big enough. They've asked you to take a look at the dig plan. For example... We got... What? We got, like, hashes? Or... Oh, color. Of course, these are color codes, hex codes. This is interesting. Oh, but we are using 2Z grids again, but... Alright. The digger starts in a 1 meter cube hole in the ground. They then dig the specified number of meters up, down, left, or right. Dig up, stupid. Clearing full 1 meter cubes as they go. The directions are given as seen from above. Oh, I see. Up means... No, okay, so really you're looking down from above and they're going northeast, southwest. Okay, fine. Each trench is also listed with the color that the edge of the trench should be painted. Why on earth would we want to do that? Oh, well, it looks like that's not relevant for part 1. Fine. When viewed from above, the above example dig plan will result in the following loop of trench. When viewed from above... Okay. Oh man, you could totally solve this in Minecraft. Or Dwarf Fortress, actually. At this point, the trench could contain 38 cubic meters. Okay, fine. So we start in an arbitrary location, and then we Okay. This is super easy. Don't even need to do breadth first or depth first. This is just literally go these steps. All right. Oh. The next step is to dig out the interior. This old thing again. That makes it more interesting. Now, I can already think of one edge case. Where you have two corners that touch. So you can't use flood fill. But we already knew that from the minecart problem, because... Well, you can use flood fill, but you can't use a single instance of flood fill. so we can probably reuse some of the knowledge we've gained from the minecart level, which I think was much harder than this anyway. But actually, Alright, see, remember when I did the minecart problem, I did a sort of point-in polygon test. And then I said if I were to repeat this problem, I would probably use flood fill, right? Starting from every interior location. So let's kind of honor that and actually do what I said I was going to do. So my idea is... Well, see, the thing is... Wait, just to be clear, does he arrive at the same place? He actually arrives where he started? Yeah, it's a loop. Alright. Yeah, so basically... Okay, so while we're walking around this loop, I store two sets. Okay, one is all the cells I've seen on my left. The other is all the cells I've seen on my right. And then when I've finished the loop, I can then decide which of those two sets is inside and which is outside. That's... We can work that out straightforwardly. Once we know that, then we do a flood fill with repeated starts. So from every interior cell that we've accumulated, we run a flood fill, breadth first search, to find all the interior pieces of that component, right? And if you do that, then you should get every interior, because every interior section necessarily touches one of these exterior loop edges, right? So it's a much simpler version of the minecart situation. Okay then. No, this looks like a nice one, and it's a not entirely trivial part one. You've got to be a little bit smart, because they will have the edge case where the corners, you have two pieces of the loop come together at a corner and then go away. So there's no space for flood fill to actually... Wait. Hang on. Yeah. Yeah. So I was trying. For a moment, I thought maybe you could use. It would take only one flood fill, but no, I'm wrong. You can actually create a loop which creates multiple segments. All right. Anyway, we're not doing a single flood fill start. We're doing repeated flood fill starts. All right. So we want to first switch the window. There we go. Um, Python. Damn it, why is the IDE taking so long? 18. I am noticing that PyCharm is getting more and more sluggish. Like, it used to be very lightweight and fast. I feel like they've added stuff that to make it really slow now. It keeps indexing stuff. I don't know. Alright, so... How many instructions do we have? Maybe about 1,000? No, looks like 100. Okay, it's more like 1,000. 618. Okay, so... how are we gonna do this? So we first... Alright. Shall I... You reuse position. This is becoming more and more useful. Let's reuse position. Because I've got all these nice methods now. But we probably won't need most of this. We don't need that. Okay. Probably won't need that either. Addition and subtraction. Yeah, we will need move. Probably won't even need subtraction. We can always add them back in. Probably won't need this either. Yeah, we do need this. Alright, so. No, we don't. If we're not using a priority queue, then we won't need that either. Alright, so, so we got a position, start equals, let's say, 0, 0. All right, we want 3 sets, okay? We want the loop. It's not that easy. This part 1. Okay, so we want the boundary. It's going to be 1 set. The left is going to be another set, and the right is going to be another set. All right. So as we walk along the loop, we accumulate these 3 things. All right. Now, every time we add to the boundary, we probably have to remove from left or right if it's in there, because you can have a situation where the boundary kind of crosses some cells which we previously thought were left or right. It is a non-self-intersecting loop, isn't it? Let me have a look at the description again. Doesn't actually say, but the fact that they're asking for an interior, well, I assume it's non-self-intersecting, because it would still have an interior if it was self-intersecting. It would just be a bit... Right, we'll assume it's non-self-intersecting. Alright, so... Okay. So we've got direction. We got integer for a number of I'm trying to think of the best way to do this. Okay. So we've got direction. Number of spaces and let's call it color. It's not quite the color, but we'll leave that for now. Equals line dot strip dot split. Okay, so our starting position is that. All right. Directions, let's say, so it's going to be up maps to -1 0, left maps to 0 -1, right, let's go in, maps to 1 0. Right 0 1. Okay, so pos equals pos 0, boundary equals set pos. Okay, we don't actually have a left right to begin with. I don't think we need one. It's fine. Okay, so now what? We need to, so let's say for each number of steps we have to move one space in the direction. So pos plus equal, so up, down, left, right. Let's call that UDLR. Direction equals UDLR. Alright, so that gets us the vector, right? And so for each of these steps, we're gonna do pos plus equal direction. Okay, so we move one step. Okay. So we move one step and now pause. So boundary, this is now boundary. So we want to add this to our boundary. But if pos in left dot remove pos. If pos in right dot remove pos. Okay. Okay, so we've updated the boundary sets. Now, the last thing we need to do is find the left and the right. So if I go in a direction, what is the space? So if I'm heading in this vector, what is the space to my right? It's gonna be you multiply by the matrix cosine 90 something or other, which simplifies to. So if you're going 0, 1, which means we're going that way. We turn right, and hang on, let me look at these. Okay, we're going up. We turn left, we end up here. Turn left, we end up here. We turn left, we end up here. So it's always going to be let's just write it out. I can't remember how matrix algebra works. Let's just say that maps to that maps to that maps to that maps to that. And this one will just be V K or K V and rotate left dots. Okay, so now we can say the left we add so it's going to be pos plus rotate left of our direction. That will give us the cell that's on our left. If it's not a boundary, hang on. Pos left equals that. If pos left not in boundary, so you have to do all this boundary checking. It's a bit messy. I guess it's fine. Okay. Rotate left direction. What? Type tuple int doesn't have expected attributes row column. Rotate left. Oh! These should be pauses. Whoops. Okay, that's made the line quite long. Okay. Alright, yeah, the IDE helped me. Alright, so now, when we finish this process, we should have a boundary and all the cells on the left and right, excluding any which are on the boundary, so... You know what would be much cleaner? Just don't remove them. Leave all the boundary cells in. And just remove them at the end. So take this out. Alright. Take that out. Take that. Take that. There we go. Let's do that. Alright, now after we've done all of this, okay, let's run that. Data class is not defined. Oh yeah, we need to import this. Pause object is not iterable. Oh yeah, whoops. All these little mistakes. Okay, we've got something. Okay. Now what? We have to so we've got all the left cells and right cells. So first, let's remove the boundary from left and right. So is set difference, is it just minus? Hang on. Left minus equal boundary. Can we just do that? Is that correct set difference? Let me test this out. Print length left. And now print it again. Yes. So it's removing all the boundaries. Because we don't need them. Okay, now we want to determine, so precisely one of these sets is the outside, one is the inside. How do we work out which one? Let's say leftmost equals, so we're going to look at the leftmost element of the boundary. That would basically be the node on the leftmost edge. So leftmost equals see, there's a catch here. What if we just by chance happen to pick the one we started with? Just assume it doesn't happen. All right, leftmost equals min. Hang on, so it's going to be the minimum of the boundary. Key equals lambda pause pos.call. Pick the minimum call. Alright, that's the leftmost. So then whatever is one space to the left of that... Oh, this could be a corner. Alright. There's a better way of doing this. Oh, so, okay, if it's corner, then this is not quite going to... How about this? Just keep going for for pos in boundary sorted boundary p equals, so we go from the leftmost cells and just keep looking until we find one which actually has neighboring spaces in our left or right. There's bound to be one, okay? Oh, I don't like this. Nah, hang on, there's got to be a better way. See, I'm tempted. See, the thing is, if I write a point-in polygon test, like I did before, to work out if a space is inside or outside, then basically all this was pointless, because I can just now use that in a for loop over all the cells. The whole point of this was to try and do this flood fill approach. Oh, maybe I should just go back to the point-in polygon test. This is... okay, this is not... I don't like this now. It's all... there's too many edge cases. It's like... Let me just have a think. How do I clean this up? I have a set. I have two sets. I've got a set that's everything to my left, and I've got a set that's everything to my right. Now I just want to work out which of those is inside and which of those is outside. And I want to just take the leftmost, because I know if I go leftmost, then anything to the left of that is definitely outside. It can't be inside, because then there'd be another leftmost, right? But the thing is, if my leftmost cell happens to be a corner, and in theory, you could have a situation where there's only two leftmost boundary nodes, and they're both corners. It made a U-turn. Then in that situation, neither would... Alright, you know what? I think we'll just do the point in polygon. I think this whole boundary thing is the point in polygon thing will be easier now, because we won't have the weird situation with the minecarts where... what was it? It was, I had a situation where you couldn't tell if you were crossing. Oh, but that might come up again. We still have that situation. Oh, man. Let's try and finish off this approach. Alright, so my idea is... Space directly to my left. Hang on. Go back to this. All right, this is the leftmost. All right. For B in boundary. So pause in boundary if pause.call is leftmost.call. So basically, I found the leftmost node, and now I'm looking along that column and picking all the nodes which are in the same line, in the same column as this leftmost. All right. Out of all of them, I take left space equals, so it's going to be B plus pause 0 minus 1, so that's the space to the left. Right? If left space in left, then the inside, we've decided that the inside is right. Okay, so that's saying if this space to our left was in our left set, that means we were going kind of clockwise when we hit this location. That means our inside is to our right. And break out of this loop. Alright. And we do the same. If left space in right, then inside equals left. Alright, so basically, as long as I do a few of these, we hope that we'll actually find the space. This is not 100% reliable though, but yeah, whatever. I think it'll work. Print inside. Alright, let's see if we actually get inside cells. Inside cells. Okay, it claims that this is the inside. Alright. Now what? We just have to do flood fill. Alright, so define DFS. For a given start set. So we start with all these locations. And in fact, it can be DFS. Alright, so Q equals, basically it's just going to be a list of the start set. These are all places we know exist. Right. Closed equals set, start set, so we don't need to repeat them. While Q, current equals Q.pop. Alright. So we pop an element from here. We look at its neighbors. So for delta in let's say directions.values neighbor equals current plus delta. Alright. If neighbor in boundary, skip this one, we don't want to cross the boundary. Or neighbor in closed, we don't want to revisit this one if we've done it before. And then we put it on the queue. Right? And then we return closed. I don't like using closed, it's a bit unclear. Should we say filled? Let's call it blood fill. Right, so interior equals blood fill on the inside layer, the layer of cells that are touching the boundary. Print. So now, okay, ultimately what value do we want? We want the boundary plus the interior. Length of boundary plus length of interior. Okay, this... Oh god, infinite loop, infinite loop, infinite loop. Alright, did we get the inside correct? Are we completely on the wrong side? If left space in left... Hello, DJ. Left space is on our left, the inside should be on our right. If left space is on the right, then the inside should be on the left. Oh, I'm never using filled. There we go. That was why it's an infinite loop. We're just repeating all the things we've repeated before. There we go. 70,253. Sounds big, but then we've got 1,000. 1,000 instructions, and they each have an integer number of spaces, so I suppose it could work. Hello, Amaro. Sounds like it could be the right ballpark. Yay! I got it right for the first time for the first time in a while. I keep getting it wrong first time. Alright, what's with the colors? What, in the input? The colors are... we don't know what they're for yet. It's gonna be for part 2, I suppose. We'll find out now. The elves were right to be concerned. The planned lagoon would be much too small. Okay, so basically this was kind of... this part 1 was basically a repeat of the minecart problem, but simpler. So the minecart problem, you wanted to compute the interior. And here, it's kind of the same dilemma, because you still have straight sections. So I could reuse the point-in polygon test that I did before. It would have the same issue where if you're crossing parallel to an edge, it's not clear whether you're inside or outside. which can be resolved the same way as before, but this time I tried flood fill approach. So as I walk around the boundary, I keep track of all the cells on my left and all the cells on my right. And precisely one of those sets will be inside. We don't know until we've closed the loop. Once we've closed the loop, we can then work out which is the inside, and then using the inside, we just do flood fill to find all the rest of the cells with all, and that works, which is good. Alright, part 2. The elves were right to be concerned. The planned lagoon will be much too small. After a few minutes, someone realizes what happened. Someone swapped the color and instruction parameters when producing the dig plan. Oh no. Oh no. Oh no. Oh no, 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 no. I don't like the look of this. Alright, one of them asks if you can extract the correct instructions from the hexadecimal codes. Each hexadecimal code is 6 hexadecimal digits long. The first 5 hexadecimal digits encode the distance in meters as a 5-digit hexadecimal number. Just fill between both ends. Yeah, but that's too many. We can't use the same algorithm. That's too big. Alright, let me finish reading. 6 hexadecimal digits. The first 5 hexadecimal digits encode the distance in meters as a 5-digit hexadecimal number. The last digit encodes the direction to dig. Okay, fine. So this gives us the true instructions. Digging out this loop. Might need geometry formulas here, yeah. So there is a formula, the shoelace formula. Which, I mean... And this could be used in the minecart problem. Some people use the shoelace formula. I meant the border. Just fill between both ends. I'm not sure what you meant by that. So we've got big stretches of lines, but apart from that, it's basically the same concept. So if there were a way to split this thing into rectangles, can we do that? It can be done using the how do you do this? I've studied this before. It's like you want to use a scanning algorithm where you scan from left and right at all the corners. And every time you come across, you can kind of split the space into rectangles, as long as you scan the the corners from left to right or up to down. I'll have to look up the shoelace formula. That might be the way to go here. Alright. Should we look up the shoelace formula then? It's just one big polygon. And every one of these describes an edge. So that should be the right stuff we need here. What the heck? Why am I having to do this? Is this appearing on stream? Oh god, it is. Alright. Fun. Don't mess up. Yeah. Everyone will find out that I was a robot after all. That normally only happens when I'm logged into my VPN, but I've never had Google search do that when I'm just doing it normally. Okay, it's getting more suspicious of me. Alright, so this is the formula basically. The base of the sum of the 2x2 determinants. I assume we want to use the shoelace formula here because people mentioned it. I don't see. So the trap. Okay, in British we say trapezium. Trapezoid formula. Okay, I just looking at them, I don't know what is best. We'll just go with this one then. The shoelace. X1, X2, Y1, Y2. So X1 and... Okay, just to be clear, X, I, Y, I are the sequence of points counterclockwise. Well, the direction won't matter. I mean, we can... Okay, fine. Counterclockwise. So we've got a sequence of points. So basically we just have to do this formula. That doesn't look hard. If I can remember how to do a determinant. Determinant of a 2x2 matrix would just be, what, x1, y2 minus x2, y1? Let's see how well I remember my linear algebra. And for, like, optimization, you could do the determinant of that whole matrix there, but that would use, like, numpy and stuff. We can just do it by hand. All right, well, let's try and do this then. So should we try and get it working on this simpler example first? All right. Alright, so we want a sequence of points. Then we can just discard all this boundary stuff. I don't like this. It's not, especially this bit here. That's a bit hacky, and I don't trust that this would even work in all cases. All right, so let's see. We simply want to record a sequence of points. Okay. So vertices equals list. Okay. Do we count 0, 0 as a vertex? Where exactly do we finish? We don't finish. Oh, hang on. Let me look at the example. Do we finish on the cell, the final on the cell we started with? Or one space before? They should really say this, because alright, I assume we finish on the same node we started. Oh wait, I can actually look at the diagram and see. Right 6 up to, yeah, we do end up on the original. Okay, good. That makes it clean. All right, so all right, vertices equals pause. That's where we start. Okay, and then all right. So before we do all this stuff, we just okay, we don't want to do this because that's gonna consume too much time. So also, I don't know why I'm doing that outside the loop. Either way, that should be it should be outside the loop. I don't know why I'm doing it inside the loop. All right, so okay, so that's the direction we're going in. So pause. So it's going to be pause is going to be plus equal direction. See, I'm going to use times here. Now we haven't defined times on a pause. We'll have to do that. Multiplying by a scalar. All right. So let's go back to the pause. We want to define multiplication. Return. So other has to be a scalar here. We don't want to multiply by another pause. So it's going to be self times other times other. Alright. So we direction pause plus equal direction. And then wherever we end up, vertices dot end pause. unless we're back at... yeah, it's okay if we insert the start again at the end. That actually is fine for the purpose of the shoelace formula. Okay. No, actually, I won't call it vertices. I'll call it boundary. No. We've already reused the boundary. Call it bound for now. I'm going to call it boundary later when we get rid of boundary. Alright, so just comment out all this stuff. Comment out all this stuff. We need that. Okay, that stuff. Yeah, this was... I didn't like this whole flood fill solution. It's not actually that pleasant at all. Alright, so just hide all this, hide everything. Alright. Define shoelace on a given boundary for I in range length boundary -1. So we've got P1, P2 equals boundary I plus 1. So this is the vertex and the next vertex. Okay, and then we got the det equals 0. The sum of the determinants. Now let me... I forget, but I think I know what the determinant is when we look it up anyway, so determinant of 2 by 2 matrix AD minus BC. Yeah, AD minus BC. And it can be negative. Okay. So we do det is plus equal it's going to be P1 dot row times P2 dot call. See, I'm trying to translate rows and columns from x's and y's. Hang on. Okay, x. So yeah, row 1 col 2 minus row 2 col 1. Okay. Okay. So we add all these up. Okay. I'm just... Okay, it's allowed to be negative. That's normal for determinants. Then I suppose we just want to take the absolute value and divide by 2. So return absolute value of debt over 2. Is this actually going to work? I'm just trusting this formula. So print shoelace bound. Well, that's not the same, is it? We had 70,253. So it's about 2,000 less. Are we... Hang on, let me print the boundary. I want to make sure we're getting that final vertex in. Maybe I'm missing one. So that we start at 0, 0. Do we finish at 0, 0? Yeah, we do. Okay. IM range length boundary -1. So that's fine. See, if I did this wrong, you'd expect the number to be way off, but it's quite close, so that makes me feel like something is slightly off, but nothing major. Pos plus equal direction times int num. See, the fact that we arrive back at 0 sort of indicates that this bit is correct. Oh, no, that's fine, that's fine. So, I don't know, let's try the most basic example, like a simple square. So, square equals, so it's going to be pos 0, 0, pos 0, 1, pos 1, 1. So this is going anti-clockwise. It's going clockwise. Pos 1, 0. And then we finish on pos 0, 0 again. So the area should be 1. Correct. If we double this, it should be 4. Yeah. Huh. So, shoelace. I mean, we could give more complex examples, but maybe the shoelace is fine. What else could be wrong? I'm worried that the boundary might be self-intersecting or something weird like that. But if that were the case, it would say in the description, surely, because then it's not... doesn't even make sense from a story point of view. Like, why would they be digging through a cell they've already digged? Because then there'd be no dirt there to dig. So, oh, of course. This is just the area, but we need to add the length of the boundary itself, don't we? Because so what we've got is the just... wait, is it the interior or... hello, Kuhani. On the sample, does it return 42? Probably not. So I think I need to add in the boundary. I can try that though. Get it working on the example. Hang on. So what we've got is we might need to... 42, yeah, it's 42, and it should be 62. So we need to add in the... is it just... do we just add in the boundary cells? I think it might geometrically, what exactly do we have? We might actually be... no, it's not. Hang on, this is not obvious. So when we dig a whole square. So what we are computing now is really as if we were we're just joining up the edges from the centers of those squares. Wait. But what we actually want is the outer edges of the squares. Wait, so what do we do then? Just... include about half of the outer square. That's what's worrying me. About half. So sometimes it'll be half, sometimes it'll be a quarter, sometimes it'll be 3/4. No. Sometimes, yeah, sometimes it'll be 3/4. Will every quarter match up with some other 3/4? No, so we've got a bunch of corners. No, they won't. How do we resolve this? So the correct way really is to work out the... The 2 by 2 you did, it would be bounded by 0, 0 to 3, 3, and you counted 0, 0 to 2, 2. Well, the square. Yeah. Just trying to think what we're supposed to do here. So, if we start at 0, 0. We actually... Man, I can't think. So every time... Okay, so... For every boundary cell, if it's a straight piece, maybe we just have to count the types of boundary cells we have. So if it's a straight edge, then we're adding half. So we need to add in we need to add in like half of that cell. And for every corner, we have to add in either a quarter or 3/4. There must be some easy way to add these up based on like some property. I've got to do something. Alright, let's think. So for every... Could we have... Okay, no, I can't. This is messing with my brain. What is the textbook approach here? I think you would want to actually draw a polygon around at the outermost point. But to do that, you would need to know... You need to know, Okay. I guess when we're drawing this sequence, we could actually record two boundaries, an inner and an outer. And we don't know which one is the inner and which one's the outer until we're done. So as we're moving... So... What number? How? What? have a look at the input again. What kind of... Is the input size small enough that we can just kind of manually... It's like the hundreds of thousands. So we could actually just walk along the boundary, cell by cell. Oh, instead of having to do something smarter. No, no, I think the input's still too big for that. All right, so I think we just have to walk around the boundary again and try to find the exact coordinates of the outside edge. I don't see any other way, so... We know the coordinates of the middles of the boundary. But I keep coming back to that idea I had before. If we know where all the boundary cells are, then for every vertex we know it's either a corner. What type it's a corner. So we would know if it's an inner corner or an outer corner, a reflex corner. If it's a straight edge, we add half of the square. If it's a reflex corner, which means it's kind of turning. Yeah, so a normal corner would be like it turns 90. A reflex corner means it's kind of turning 270. Then we would add in 3/4, and if it's a normal corner, we add in 90. We could do this, can't we? You just look at the geometry of it and see which type of corner it is. Maybe we just do that. So, all right. So we need to add in the boundary now. So we know what the interior is. We need to now compensate by adding in the boundary. So I trust my shoelace formula. Okay, so interior area equals shoelace bound. Should we just... Yeah, okay. Now, okay. Compensate by adding in area from boundary cells. Alright, so we go 4. So do this again. Hang on, so the edges, we don't need to do anything about that. We've added in the correct amount for the edges. It's just the corners we need to deal with. So on the normal corners, 90-degree turns, we have added in a quarter, and we should have added in... I'm so lost. Maybe I need to do a diagram here. Let me look at the website again. This example they've got. So yeah, okay. Alright. Alright. Okay. I get the geometrical situation now. Alright, so P1, P2 equals... Alright, let's just rename this to boundary. Factor, rename. Alright, so we've got a vertex and we've got the next vertex. So we've got a line segment. Alright. Alright, no, let's not do it like this. Let's say we want to look at the corners. Let's deal with the corners first. For I in range, so, okay, so for I in range length boundary. Okay, so we look at all the boundary cells one by one. I want to work out what kind of corner it is. How do we do that? We have to work out what kind of turn we made to get from... Okay, so previous equals, it's going to be... So, okay, so current equals boundary I. Previous equals boundary I minus 1% length of boundary. Next equals... We're not supposed to use next. Okay, previous node, next node, current node. Here we can just say I plus 1. Alright. How do you work out what kind of angle this is? I think we don't know whether you which side's the inside. Well, you have to... Oh. I don't like this approach now. I think maybe the best way is to just, when we are drawing the boundary, we actually keep track of an inner and an outer. Alright, so how do we do that? Let's see if we can do that. We want an inner boundary. Well, we don't know which one's inner and which one's outer. Okay, so it's going to be boundary 1, boundary 2. Okay, so when we start, we don't know which one's inner and out because we don't have a notion of anything. So when we start, we've got to. Alright, we're not keeping a boundary anymore. We're keeping boundary 1 and boundary 2. Alright, so when we get our pause, and we know where we were previously. Alright, so wow, I'm seriously confused. Should I whip out Microsoft Paint? I need to start drawing some diagrams here. Alright, so the problem I'm having is I just don't get what to do about. So let's say we have this simple example, right? So that is a bunch of points. Right? But what we've actually got, and we can compute that area, that's fine. But we're missing the boundary. What we've actually got is these. Okay, so if you look at each of these, we have to compensate for these because we've gone over or under. So we've computed this area, but what we actually want is the area enclosed by this outer set of lines, right? That includes the boundary. Okay. This is helping. I should have started doing this diagram from the beginning. I need some food as well. Alright, so what we have for each of these corners, we have a bit. We've calculated a bit of it, but we haven't got the other section of it. And it's either we've already got a quarter of the cell, and we need the other 3/4, or in case of the reflex ones, we have 3/4 and we need to add in the quarter. Right? So once we have the polygon, we just have to work out which one of these, which of these are reflex, which ones are normal. So this is like a normal one. These ones, that one, and that one are reflex corners. Once we know that, we can just so for the edges, so for each edge, so for an edge, we can actually just, between two vertices, we can add in this area here, which we know is going to be 0.5 times the length of that edge. Okay, and that, if we do that for all the edges, then we'll end up doing something like this. It's really just a question of how much we've gone over or under, and compensate it by checking each of the corners and adjusting as necessary. Okay. All right, so let's do these pieces as we go along. So we add up all that shaded area. That's easy. No decision there. It's just for each edge we just add in 0.5 times the length of that edge. Okay. And then we then look at the types of corners. For all the kind of like the normal right angle corners, we are missing a quarter, so we have to add in 0.25. And for all the reflex corners, we have added extra quarter, so we have to subtract 0.25. So that's what we do, right? Should we just do that then? I mean, the hardest bit is working out what kind of corner each corner is, but I mean, it's not impossible. We can do that. All right. That helped. I think I can now do something. Alright, let's go back to this. So corners, yeah, don't do this yet. Alright, so first let's add all the edges. Alright. So let's say area, because interior is misleading now. Alright, so for straight edges, so we go here. Right. And then we simply area plus equal. It's going to be 0.5 times let's bring back the Manhattan distance. So we can use that here. It's going to be 0.5 times P1 dot this P2. So this is going to be... We don't want this to be an integer now. Let's say... Well, that's going to make it a float now. Let's see if that runs. Boundary. Oh yeah, we don't want to do this boundary 1, boundary 2 stuff. Let's forget about that. Print area. So let's print area at each stage. I just want to see what is happening to it. Okay, so we've added in that area. That gets 61. Remember, the answer we're going for is 62. Alright. And now we need to handle corners. This is the bit which is confusing the heck out of me. Alright. How do we work out what kind of corner a corner is? Is this... You want to do something with the winding number or something? Alright, so we know what the previous, we know what the next, and the current. Okay, this alone doesn't actually help. Alright. We know that the top left corner, so if we go leftmost and then go upmost, we will arrive at a corner which absolutely must be a regular 92-degree corner, so it's non-reflex. Is that true? And if we go from there, fuck. Oh my god, this is so confusing. So that tells us one corner and whether, okay, we know where the interior is. If we then walk If we then walk along these vertices, we know where the interior is. It's always to our right if we're walking clockwise. So that would mean every time we make a right turn, okay, I think I can do this. All right, we don't really want to do this. We want to say top left corner equals minimum boundary. So we're trying to find a vertex, which is basically lambda e. So we're gonna prioritize minimizing the dot col and then the p dot row. So this is necessarily a corner where the bottom right of that cell is the interior. Like, there's no situation where that can't be true, right? And minimize, if I take the leftmost and then go upmost, that has to be, and there can't ever not exist such a corner, right? You always have to have such a corner. So, so that top left corner, we know we have a starting point. So from here, we can see every time we make a right turn, wait, is this boundary going clockwise or anti-clockwise? Oh, there's too many things we need to keep track of. So now, I think Well, we've got to do something. Let's say I equals boundary dot find. Well, there's no find method for a list. Dot index. Top left corner. So that just tells us where in the boundary top left corner is. Right. So now create a new boundary. B2 equals. It's going to be boundary from I onwards. Ignoring the last position because we've duplicated the vertex there, and then plus the left hand part of the boundary, so it's going to be up to I. So I'm sort of reconcatenating it, pivoting around this. So we want this I to be the first position. So we do that from I onwards. Okay. And then just add in I again, so that we've closed the loop. Alright, so now we've basically pivoted the boundary around I. Going back to the shoelace you did earlier, getting area 42, the perimeter is 38. 38 divided by 2 plus 1 equals 20. What? The perimeter is 38. Okay, first of all, where do you get the perimeter? You just add up. Okay, perimeter we can work out easily. Just add up the lengths of the edges. Divided by 2 plus 1 equals 20. So what, you're saying the formula for the amount we have to add is simply the perimeter divided by 2 plus 1? Why? Why does that, if that works, why on earth does that work? I don't know. Is there some clever pattern here, like every reflex corner matches up with I can try this, but geometrically I don't understand why that would work. Maybe it's something like, oh, it's something to do with winding numbers. Maybe the number of reflex edges you take has to for every reflex edge you take, you have to take one additional. Oh, there's some clever pattern here, but I can't reason it out. All right, let's try it. Because I don't like doing what I'm doing right now. So perimeter is Okay, we can work out the perimeter here. Perimeter equals 0. Or we can work out the perimeter up here. So boundary perimeter plus equal. So it's going to be just num. And you're saying we should do area plus equal perimeter. Should this be a floating division? So divided by 2 plus 1 and take the int of that. $62. Yeah. Okay. I mean that formula just come out of nowhere. Alright, I'll try it. Fine. Let's try it on the big example then. 70253. That's correct. Why does that work? I don't understand that formula at all. Perimeter divided by 2 plus 1. Alright, should we just... whatever. Before I try to figure this out, let's just try it then. So now we need to do the boundary for part 2. So boundary 1. So let's call this... boundary 1, perimeter 1. Hang on. Okay, so we've got boundary. Okay, so that's part 1. Alright, part 2. So we're taking this should work then, because we're taking the same corners. Man, that's crazy. I don't understand this. Alright, well, we can get rid of all this stuff. We're not going to be using this again. Did we even use dist? No, we didn't. So... get rid of all this stuff. Alright. Okay, so, yeah, we don't need dist either. Alright, so part 2. So we've got the color. Alright. Hex code equals, so the color of those 3 digits. So it's going to be color 2, and then ignore the parentheses at the end. So it's going to be like 2. Alright, so color hex code equals that. So the first 5 digits of the hex code. So let's see. First 5 is the distance in meters as a 5-digit hexadecimal number. Alright, so the first 5. So hex code from to 5. We want to turn that to an integer. Decimal, so it's, let me Google this. It's, you probably use int with something parameter. Use int with basic 16. Yeah, okay. So it's int of that base equals 16. Is that right? Or have I got this the other way around? That's right. Yeah, it's that's how you do it. Okay. So that is the distance. So and the final digit so it's gonna be basically so they said 0 maps to R. Going to leave spaces, fine. 1 maps to D. 2 maps to L. 3 maps to up. So it'll be that on hex code -1. That gets us the, yeah, that's fine, the ULDR2, and then as before we take direction 2 equals direction UDR2, and then we just do all this again. Pos 2 plus equal direction 2 times num2 boundary 2 dot append pos 2 perimeter 2 plus equal num2. Pos 1 pos 2 equals that. That's part 1, part 2. And then what? Just do all this again for... Oh, this is crazy. that. Crazy big number. All right. Let's try it out. It should work because if it works for the small case, the large case is just the same shape. It has the same corners, just scaled up. So if it works for the small case, I don't know. I don't understand why this works. Draw it on paper. All right, I'll have a look at what Kuhani has posted here. I get that there's probably some really straightforward pattern that, so all that stuff I was saying about reflex corners and stuff probably cancels out because the number of, it's to do with winding numbers, isn't it? The number of right turns you take is going to be the number of left turns minus 4 or something. Every time you... Okay, so if you're going clockwise around the edge of a shape, every time you take a left turn, you're going to have to take one more right turn to compensate for that. So ultimately, you take 4 right turns to get back to where you started, which would form a perfect square. But if you ever took a left turn, you'd have to have one more right turn. So the number of right turns will be number of left turns plus 4. So the number of times... So then if we do go back to what I have with the paint... Okay, I'll have a look at your image in a minute. So if we go back to what I was saying about the paint... in the paint diagram, I was saying we overcompensate, we undercompensate on these normal corners, and we overcompensate on these reflex corners. So if the number of the perimeter divided by 2 is the shaded area. All right. Then you're adding 1. That adding 1 accounts for the 4. Okay, I'm starting to see the pattern now. If it was a perfect square, perfect rectangle even, you go around clockwise like this, right, starting from here. You make 4 right turns, right? So the perimeter, if you add in the perimeter divided by 2, you get this shaded area, this shaded area, this shaded area, okay, this terrible diagram, and this shaded area, okay. So the bits we're missing are these like little corners here, 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 and here. So you're adding 1 because those 4 corners all add up to one whole square. So in a perfect rectangle, the formula is perimeter divided by 2 plus 1, as you've said. Okay. The problem is whenever you add a reflex corner, it distorts the shape. But for every reflex corner you add, you have to add one more regular corner to bring you back. Okay, so even if you add lots and lots of windy parts and stuff, it always means if you add one more left turn, you have to add one more right turn. And they cancel out. Because as I said, every right turn is kind of an undercompensation, and every by 0.25, and every left turn is an overcompensation by 0.25. So they cancel out perfectly. So yeah, that's it. It works. The formula is perimeter divided by 2 plus 1. That's blown my mind. I mean, if I was messing around with this long enough, maybe I would have spotted the pattern. But it's not exactly easy to come up with that formula. But once you're given the formula, it's kind of straightforward to verify that it is in fact true. Okay. All right. Let me have a look at what these links you've given me. So sorry, I need to copy. So I need to sandbox these links, you know, that's good practice before I actually show them on stream. Alright. Alright, so alright, so this is what Kuhani has showed me. So this is essentially the rectangle, the easy case, right? And then I guess, I don't know if you've actually reasoned out the thing about the reflex corners, but yeah, reflex corners don't alter. Adding in reflex corners doesn't change the area, because every reflex corner gets cancelled out with another corner. Okay, this is Zombie Killer Whale's Python solution. Pick's theorem. Ah, so you've actually done the thing about concave corners and convex. That's the term I was looking for. Concave and convex corners. Reflex corners is correct though, but I prefer convex and concave. Right. So you've actually found those numbers. So that was kind of what I was trying to do until Kuhani saved the day with this magic formula, which I've now proven is correct. But sorry, what's Pick's theorem then? I've heard that before. So. Oh, it's just a simplified version of shoelace where you know you're at integer corners. Hang on, so I don't need the shoelace formula at all. Okay, so I is the number of integer points interior to the polygon. Oh, so I guess you do need the shoelace formula for that. Let B be the number of integer points on this boundary. Interesting. So it's a generalized theorem that would apply to weird shapes like this. So in our case, but it is actually what we're looking for, because we have. This is good. I'm gonna have to remember this because it could come up again. See, this second diagram here is more useful. It pertains more to our situation. Not quite though, but. Alright, I don't need to memorize Pick's theorem, I just have to remember that it's a thing. So what we had was, okay, so the number of integer points interior, is that precisely what the shoelace formula gave us? Hang on, but we're adding. Maybe I should look at your code, see what you've done with that. Picks. So this explains how some people used. Oh, I see. Okay, so Pick's theorem doesn't quite match the formula we had. It's just you just gotta, because these variables are slightly different from what we had. Number of integer points on the interior is not exactly what the shoelace formula gives us, but we can probably work around it and get it. All right, I guess I won't delve into this on stream too much. I mean, I've proven one formula, and that's good enough. But yeah, this is interesting stuff, and I think I should look into it because it might come up again. I mean, has it ever come up in Advent of Code before? Doesn't matter, it's still important to know, but it might have come up one or two. Oh, well, actually, some people use Pick's theorem for the minecart thing. I seem to remember it being mentioned. Yeah, I know people were using the shoelace formula for the minecart. I didn't know about... Alright, well, it's come up twice then, so I guess... Planar graphs. Oh. Alright, I'll do some reading on that. So, wow, that just makes it a lot simpler. Now I see why. I mean, well, okay. Let's have a look at the. Let's have a look at the leaderboard. I bet people have done this really quickly because if they knew that, if they just plug that in, then that's pretty straightforward, isn't it? 5 minutes 31 to do both parts. Yeah. That's believable. Two minutes 35 to do part 1. I guess part 2. I mean, you just plug it back in, but part 2 you'd have to just do the thing with the hex codes. I would have thought you could churn that out quicker than 3 minutes, but maybe not. Okay. Well, you still got to read the problem. All right. Well, we've done it. Amaro is catching up, so I'm guessing Amaro did the Dijkstra algorithm. That one seems like it might be suited for the game engine that Amaro was using to code in, but it's still very custom, so you have to be smart about your state space. Oh yeah, I'll paste the leaderboard code in to chat if anyone wants to join onto the leaderboard. And I think that's taken me long enough that Captain Coda could be streaming, or maybe a couple of other people that have been following their progress. Let's have a look. I'm not logged in. Captain Coda is not live. He's probably going live in an hour's time. Let's see who else. Coda 2K is using... I wish people would put their language in the title. I feel like that's... We should really do. Is this Python? Yeah, it is. Alright. Wait, what language is he speaking? German. Okay. And I'm speaking English. This is 18, right? Day 18? Yeah, okay. We, raid this guy one up time. Alright, well, go have a look at what 1UpTime is doing. Maybe he's stuck on the same bit that I was stuck on. That was one of the toughest problems. If you didn't really know that geometry stuff, I would say. Like, that is not easy. That's needs some original thinking right there. So that was a good problem though. And it's satisfying once you know there's an easy way of doing it. So yeah, okay. Well, see you guys tomorrow then. For day 19, probably around the same time. I might try and start earlier. I usually try and start bang on time as the problem releases, but I don't always manage. What I tried to show to get area of 2x2 boundary blocks was actually 3x3. I think one of the quad being attached to the lower left corner, so including 3 perimeters and leaving 5 outside. Yeah. Okay. Alright. See you guys next time.